Ladies and gentlemen, welcome to part 3, and we're gonna continue rocking and rolling with this W.E.D unit. How's the holiday going, by the way? Okay, so far we've covered weathering and we've covered sediments, the different kinds of sediment based on arrangement, sorted and unsorted, and based on shape, angular and rounded, and based on size, boulders, pebbles, clay, silt. Before we get into erosion again, I want us to have this part 3 where we're going to cover how sediments are transported, the methods by which sediments are moved from one place to another. And also we're going to be looking at stream velocity and how the velocity of a stream can determine how what sediment size can be moved from one place to another. All right, enough talking and let's get right into it. So we established earlier on that a river has a course. You have the upper course, or the source from where the river is flowing from, and we said rivers typically would flow from a higher elevation to a lower elevation. And at that higher elevation, because of the steepness of the slope, the river flows down quickly, fast, with a lot of energy, with a lot of speed, a lot of velocity, and as a result, at that upper course of a river, the river is able to move heavier and bigger sediments. But as a river gets to the lower course, or to the old age or old stage of the river loses strength and loses speed, because now the river is more in a flat terrain, in a plain. So the slope is not as steep as it used to be anymore. So there's a drop in velocity, and then there is a drop in speed, and as a result there's a drop in energy, and as a result the heavier loads are deposited and only the tiny small guys are transported further. So because of that weakness, the river begins to meander. All right, by meander we mean the river begins to move in a very snake-like manner, as you can see in the picture to your right. So this bending of the river is what you call meander, and we're going to cover that in a little bit as well. So this is like a cross-sectional view of what a river is, from the source, the mountain, all the way to when it's going to join the ocean. Now, be mindful of the cognizance that even though this is an overly simplified model, the length of an entire river can cross thousands of kilometers and thousands of miles, crossing several countries or several states. So this is quite a stretchy expanse of space or region. We're just trying to simplify it here in this model. All right, and we know in the upper course of a river you have things like your waterfall, right? And then another thing that is also created in the upper part is what you call a tributary. All right, it's from the word contribute, to pay tribute, to join something. So when a smaller river joins a bigger river, it is called a tributary, because the smaller river is paying tribute to the bigger river. The smaller river is contributing, all right, it's making a contribution to the bigger river, hence the name tributary, to contribute, to pay tribute. Then you have march, as march is like a swampy kind of area in the middle course of a river. And then you have Oxbow Lake. Oxbow Lake is a lake that has been cut off from the meander. A little bit of that as we go on, and then we just discuss the meander, which is the snaky bending movement of a river as it enters its middle age into the lower course of that river. Next you have floodplain. Floodplain is the area close to the river. If there is excessive rainfall, the river can expand and cover and flood that area. That is why it's called floodplain. And then you have the delta. Delta is when the river splits into several smaller rivers before it joins the ocean. All right, a little more of that here. Again, you have the source of the river, the upper course of the river, where the river is flowing to a lot of energy and can carry a lot of load big sediments, and lakes can be formed here as well. That's why in the mapping unit we said lakes and rivers can have altitude, however can have height or can have altitude. They can have contour lines that are above zero. But when it comes to the ocean and the sea, their contour line can only be at zero. All right, so it's possible to have a lake up in the mountain, or a pond up in the mountain, or have a river up in a higher ground, but oceans and seas are always at sea level with a value of 0, because that is the reference point from which all other heights are measured. Rapids, we all know what rapids are, where the energy is, when the river is flowing with a lot of energy and a lot of a lot of turbulence in that area. We know what waterfall is. We are very familiar with what a waterfall is. This is a tributary, again, a smaller river joining a bigger river, paying tribute to that bigger river. Floodplain is the adjacent land close to the river on both sides that is liable to get flooded when there is an influx or an increase in the volume of the river due to seasons or due to excessive rainfall. So that area is liable to flooding, hence the name floodplain. Then you have your Oxbow Lake. Oxbow Lake is as a result of excessive meandering of the river, when the river begins to snake all around, and then as a result of the excessive snaking, it can end up being cut off. And then you have a little Oxbow Lake being cut off there. Usually it's like a bowl, hence the name Oxbow Lake. Then you have Delta again, when the river splits into several smaller rivers before joining the ocean. Now, those are popular landforms that are produced in the course of a river. Next is your ERST, page 6 again. I think we're getting more and more familiar with this diagram now, and we already established the different kinds of sediment sizes here. Next, I want to introduce the stream velocity, the speed of the stream, the velocity of the stream, and what that velocity can carry at certain different speed. Now, you will notice that the speed of the velocity of the stream is increasing to the right. All right, so this means that if a stream, for example, is having a velocity of 100 cm per second, that is the speed of the stream. It means that stream, you have to trace that 100 cm up, and then until you get to this curve, this thick line. All right, we're gonna call it the curve. So when it gets to the curve, it tells you what particle size it can carry. So at a velocity of 100, and you draw it up until you hit that line, it means if you draw it this way, it means the river can carry some pebbles. All right, at that speed of 100 cm per second, it can carry some pebbles. And if it can carry pebbles, definitely it can carry sand, it can carry silt, it can carry clay as well. All right, let's take another example. Say the velocity of a stream is 1. What kind of sediment can that stream carry? So you're going to take 1, and then you're going to draw it up until you meet the curve. And once you meet the curve there and you draw it this way, you can see that at that velocity, that stream can carry some sand, not all sand, but definitely some sand, and then some silt, and then some clay at that velocity. A little practice with that, you're going to get a hold of it. All right, next we're going to talk about the method of transportation, how sediments are transported. In this case here, you can see obviously this is a wind carrying out this transportation. The first method here is called the saltation. Now, saltation is when the sediment being carried hits the ground, bounces off, and then hits the ground again, and then bounces off again. That is saltation. All right, to somersault. All right, to hit the ground and then bounce, hit the ground and then bounce off. Now, when it hits the ground and breaks into smaller pieces, as you can see in the picture, it is called attrition. All right, which means to break into pieces. Attrition. Next is it's called traction. Traction is when the sediment is not bouncing, but rather is constantly rolling on the floor. So if you look just all the way at the back, you see some kind of traction going on there. That sediment is just being pulled along the floor. That is called traction. The other one is suspension. Suspension is when the sediment does not get to the ground at all, but is constantly being moved in the medium carrying the sediments without hitting the ground. To suspend it, all right, to be suspended continuously without hitting the ground. This will draw a little more clarity to it. Again, traction is when it's constantly being moved along the floor without leaping from the floor. Saltation is when it lifts from the floor and then hits the ground again and then lifts up again. That is saltation. And then you have suspension, is when the sediment is just constantly being suspended from the floor. And then you have the last one, solution. Solution is when the sediment or the mineral itself dissolve completely into water, that you don't even see it, but it's being transported because it has dissolved into water. Just the way you have your cup of coffee and then you have sugar in it, but you don't see the sugar, but the water is already carrying the sugar because it is completely dissolved in the water. All right, let's wrap it up here one more time. Traction, when it's being pulled along the ground. Saltation is when it bounces off the ground and bounces back off. Suspension is when it's constantly above the ground. And lastly, solution is when you can't see it because it has been dissolved in the water. So let's answer these here. Process C, what do you think process C stands for here? C obviously is being dragged along the floor, that is traction. What do you think process B here? Process B is bouncing off the ground and then hitting the ground again, that is saltation. And then process A is constantly above the ground, that is suspension. And then when these break into smaller pieces, is called attrition. Now there's another one here called abrasion. Abrasion is when the sediments being transported begins to form a round smooth surface as a result of prolonged transportation. So the rough edges are being cut off or are being smoothened to form a smooth or a rounded sediment. That is called abrasion. All right, and I think that ends part 3 for us. Quick one. So as usual, we're going to answer some Regents question here and then we wrap it up. Question number 1 says, which particles will be transported by a stream moving at a velocity of 5 cm per second? We're going to need our ERST page 6 for this lovely diagram here. So the question gave us 5 cm per second. So if we follow that 5 cm per second and we follow it straight up to that line, and whenever we hit the line, we're just going to take it the other way. All right, and then we can see that at that 5 cm per second, that stream can carry some sand, and then if it can carry sand, it can carry silt, it can carry clay as well, because clay and silt are smaller than sand. So any stream that can carry sand can equally carry silt and clay. So we are looking for sand and everything below sand. That would be our correct option. So pebbles, definitely not. Pebbles will be too big. Sand, silt, and clay only. It does sound like B. Let's look at C. Silt and clay only. No, it can carry sand according to what we saw. So this is out. Clay only, that is out. Our correct answer here is B. Question number 2. On the Earth's surface, transported materials are more common than residual materials. All right, transported materials when it's being brought from another area, than residual materials, a material that is local, that is originally resident, from the word resident, residue materials. This condition is mainly the result of, all right, so what it's trying to say is that most of the things we see in our area on top of the soil are not originally from this area. They were brought in from somewhere else. So any material that we see that is not a local material must have been transported, must have been brought in from another area. So the transporting of sediments is what we call erosion. So our answer here will be erosion. So all those sediments were eroded or were transported from another part of the earth to where they are. Question number 3. As a quartz pebble is transported by a stream, the pebble will become more rounded as a result of All right, when a pebble or when a sediment is becoming more and more rounded, it's as a result of abrasion. All right, we discussed that moments ago. It's as a result of abrasion. So we go with abrasion by colliding with other rocks. Yeah, definitely. So by colliding with other rocks, the rough edges are taken out, and then it becomes smoother and smoother and smoother as a result of long transportation and colliding with other sediments. So the sediment over time becomes rounded and becomes smooth. So abrasion is responsible for that. All right, question number 4 here. La 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 la, and then we have that lovely diagram there, and the main question says, what is the largest type of sediment that could be transported at location B? Location B is right here. Distance from source is 40, and elevation from sea level is about 500, and here it gives us the stream velocity. The stream velocity is 110, and it's asking what is the highest size. So when a stream is 110, let's look for that. I see 100 here, and this is 100. 110 has to be something a little bit above. Remember, if this is 100, this is 200, right? And this is 300, 400, and 500. So 110 will have to be something really close to 100. And if we follow that line up until we get to that curve, and once we get to the curve, we go to the right, then we can see that the largest size that can be carried here would be pebbles. All right, would be pebbles right around there. So let's see. Yeah, option C, pebbles will be the largest that can be carried. All right, question number 5. The composition of sediments on Earth's surface usually is quite different from the composition of the underlying bedrock. This observation suggests that so the sediments on the Earth's surface, they are different from the bedrock, which means the rocks that are under, all the way at the bottom of the Earth in that area. So if the sediments above or on the surface are different, it's because they were brought in. They were brought in from somewhere else. So which means the sediments were transported from another part. All right, there. Yeah. Question number 6. The block diagram below represents a portion of a meandering stream. We know what a meander is, when the river is snaky all around. Meander stream, and the valley it has produced. So the meander has produced this depression that we see around here. One landscape feature is labeled A. So this the floor of the depression there is called A. The landscape feature labeled A is best described as, remember we said the land close to the river on both sides that are liable to flooding is called floodplain. So that is what this area definitely will be, because if there is excessive rainfall, there's an increase in the volume of the water, the river will expand to cover those areas and flood those areas. As a result, it's called a floodplain. Question number 7. A river transports materials by suspension, rolling, and suspension when it's suspended, not touching the ground. Rolling when it's rolling on the floor, called traction. And then solution when the sediment is dissolved completely in the water. So definitely it's not sublimation, it's not transportation, it's not evaporation. Our answer here is solution. All right, question number 8, and I think that's the final answer. Quick statement is most accurate description of condition in both streams. So we have stream 1 here, and then we have stream 2 here. You have point A, B, C, D right there as well. And I can see that A will be the source where the river is flowing way faster, and then D will be the mouth of the river where the river joins a bigger water like a lake or an ocean. As a result, most deposition will take place at D. So which of the statement describe both condition in both stream? The greatest deposition occurs at B. No, the greatest deposition will occur at D, where the velocity of the stream will be the lowest, and as a result it will drop more sediments there. So A is out of the way. B cannot be where the greatest sediment will be, greatest deposition will be taking place. Option B, particles are carried in suspension and by bouncing along the bottom. Yeah, that's how typically any river, regardless of the velocity, that's how they carry all their sediments, by suspension, by saltation, by traction or rolling, and by solution. Option C, the particle will have greater velocity than the water in the stream. No, the particle cannot have a higher velocity. It is the water that is pushing the particle, so they will have both velocity, or the water will even have a higher velocity than the particles. So definitely not option C. Option D, the velocity of the stream is same at point B as at point C. No, the stream cannot have the same speed at B and C. C will have a lower speed, so D is out of the way. So yeah, our answer definitely is option B. Alright, gentlemen and ladies, that's a wrap for part 3. See you in part 4. Bye for now and enjoy your break.